Very good morning, students. Now we will continue the amplitude modulation. Now previously we start with the amplitude modulation and thereafter we just see the double sideband suppressed carrier modulation technique. Okay. Now this session we start with the derivatives of amplitude modulation, which is ssb-sc modulation. Okay. Now you tell me, in amplitude modulation what are the problems we are facing? Bandwidth. Okay, our main ultimate aim is to reduce the bandwidth. So in AM bandwidth is 2 omega. Amplitude modulation, the bandwidth which is 2 omega. Now our main aim is to reduce the bandwidth. The bandwidth of the modulated signal should be as minimum as possible. So for reducing a bandwidth, I have to go for another modulation technique, which is dsb-sc, whereas I may expect the reducing the bandwidth, but unfortunately the bandwidth of dsb-sc is also same, right? So the AM and dsb-sc bandwidth is same. So with respect to bandwidth, there is no improvement in dsb-sc, and of course one power component is saved. Therefore, efficiency is increasing in dsb-sc. So efficiency, power saving, all are important, but the main important heart of the communication system is nothing but bandwidth. So I want to minimize the bandwidth, because a bandwidth of the modulated signal should be as minimum as possible, such that I can accommodate more number of signals through the channel, is called as multiplexing. Okay. So in dsb-sc there are two sidebands. So what I am doing is single sideband suppressed carrier. Okay, so here double sideband suppressed carrier. Now here there are two sidebands. Now one is upper sideband and another one is lower sideband, right? Two sideband, upper sideband and lower sideband. But in single sideband, what I am going to do is to minimize the bandwidth. So here upper sideband or lower sideband, only one sideband. Okay, whether upper sideband or lower sideband, only one sideband is transmitted through the channel at a time. Okay, whether upper sideband or lower, both are symmetrical, not a problem. Okay, only single sideband, already carrier is suppressed. So what should be the bandwidth? Okay, we'll find. And here in AM, the total power, which is equal to the power carried by carrier and power carried by upper sideband and power carried by lower sideband. Now the another name for AM, there is another name, earlier also I am explaining, AM or double sideband FC. Don't confuse in the question. Sometimes the dsb-fc modulation, he is giving the questions like this. dsb-fc modulation is double sideband full carrier. Here carrier is present, full carrier. Now these two are not same. Double sideband full carrier means AM. Now double sideband suppressed carrier. This is not full carrier. No, here it is suppressed carrier. Okay. Now this is here. Now this carrier component is suppressed. Therefore the total power is nothing but upper sideband power and lower sideband power. Okay. Now what about here? Bandwidth we need to find, and the total power which is equal to the power taken by single sideband. The total power equal to only one sideband, whether upper sideband or lower sideband. Therefore that single sideband, which is nothing but whether it should be an upper sideband or lower sideband, only one sideband at a time is transmitted. Okay. So obviously there is no confusion in all suppressed carrier modulation techniques. Definitely the power efficiency or modulation efficiency should be increased. Am I right? Why? Because whatever the total power is carried by the sidebands, whatever the total power is carried by sidebands, whatever the total power, now that is the power which is nothing but the total sideband power. There is no carrier power. Sidebands will take more power, and obviously power efficiency is increased. Okay, so we'll find what should be the bandwidth in ssb-sc. Now whether you get the achievement of reducing the bandwidth or not, we will find. Okay, before that you just write this. The mathematical time domain equation of dsb-sc is AC AM by 2 cos 2 pi FC plus FM into T plus AC AM by 2 cos 2 pi FC minus FM into T. Now this is double sideband suppressed carrier time domain equation. Now this is upper sideband and this is lower sideband, right? So, but what is our equation? Our equation is a single sideband suppressed carrier. Now the single sideband suppressed carrier is S of T of single sideband suppressed carrier, which is equal to AC AM by 2 into cos 2 pi FC plus or minus FM into T, where here this plus represents ssb-sc with upper sideband, this minus represents ssb-sc with lower sideband, whether it is an upper sideband or lower sideband, not and or. Okay, so if I expand these equations, see here what should be the changes. Now S of T of ssb-sc, which is equal to, if I expand this equation, AC AM by 2 cos A cos B, cos A cos B, this plus becomes minus, minus becomes plus, AC AM by 2 sin A sin B. Now see here, S of T of ssb-sc, which is equal to AC by 2. Now AM cos 2 pi FMT, you can write it as M of T, right? You know that, into cos 2 pi FCT. Now this is minus or plus AC by 2, AM sin, this is AM cos, this is AM sin, 90 degrees phase shift. Now this is called as M cap of T into sin 2 pi FCT. Here you just see here, what about here, what is minus and what is plus here? Here minus in this equation, now this is expanded. So in this expanded equation, now this plus will become minus and minus will become plus. Therefore here this minus is nothing but, this minus is nothing but upper sideband. Now this plus is nothing but lower sideband. This minus is nothing but upper sideband. This plus is nothing but lower sideband. Now see here. Now sir, what is that M cap of T? Now just M cap of T is Hilbert transform of, M cap of T is Hilbert transform of M of T. M cap of T is the Hilbert transform of M of T. So M cap of T, which is equal to Hilbert transform of M of T. So now see here, now what is M of T? Now which is nothing but M of T is AM cos 2 pi FM into T. M cap of T is AM sin 2 pi FM into T. Now this is a cos and this is sin, which is a 90 degrees phase shift. Okay, Hilbert transform is a 90 degrees phase shift. Hilbert transform of cos is sin. Okay, now this is a see here. Now this is ssb-sc. M of T is nothing but AM cos 2 pi FMT. This is a single tone ssb-sc. And what about this? This is M of T ssb-sc multi-tone. This is multi-tone and this is replaced, therefore this is nothing but single tone ssb-sc, right? So this is a mathematical time domain equation of ssb-sc. Okay, now this is upper sideband or lower sideband, so I just write this is minus or plus expanding that, therefore this is multi-tone and these are nothing but the single tone equations. This is single tone SSB, but AM cos is nothing but M of T. M of T, when I replace with M of T, then it will become multi-tone. Hold on. All the modulation techniques what we studied so far. AM. What is AM? In AM, the total power equal to carrier power plus upper sideband power plus lower sideband power. So, therefore, the total power which is equal to PC into 1 plus mu square by 2. This is a power distribution in AM, amplitude modulation. Now, what is the power distribution in DSB-sc? Now, this is the double sideband suppressed carrier. The total power equal to carrier suppressed, and this is upper sideband power and lower sideband power. So, here the total power which is equal to PC into mu square by 2. You know that. Now, what is the power distribution in SSB-sc? In SSB-sc, the total power which is equal to only a single sideband power, whether upper sideband or lower sideband, which is equal to PC into mu square by 4. These are the power distributions in a different modulation techniques what we covered so far. Am I not? So, what we can identify from those power distributions? Okay. Now, what is the point you can arises from these three modulation techniques? If you observe, now here the power distribution in the three components, carrier, upper sideband, lower sideband. But here the power is carried by only sidebands. Means when you come to AM to DSB-sc, one component of power you saved or not? Yes. Therefore, now we want to find power saving. Power saving. What is a power saving? Expressed in terms of percentage. Saved component power. Which component power you saved? Saved component power. Over a total power, how much power? Over a total power, which component power you saved? Saved component power by total power is nothing but percentage power saving. Okay. So, this is the power saving. And now we'll check one by one. Now I'll start with what is the power saving? What is, write one question also, not a problem. What is power saving? What is power saving in DSB-sc when compared with AM? Let us have one question like this. So, what is the power saving in DSB-sc when compared with AM? Now come to here. In AM, the power carried by three components, but in DSB-sc, now power carried by two component means one component power you saved in DSB-sc or not? Which component power? This carrier component power you saved. Therefore, now see the power saving. So, the power saving is nothing but the saved component power. What is the saved component power? The saved component power is a carrier component power you saved out of the total power. So, this is the power saving in DSB-sc. This is the power saving. So, which is nothing but PC by what is the total power? PC into 1 plus mu square by 2. PC cancel, which is equal to 2 by 2 plus mu square, which is equal to a function of modulation index. This is the function of modulation index. 2 by 2 plus mu square, which is a function of modulation index. This is the power saving, am I not? So now I am asking question, what is the maximum power saving? So the maximum power saving which is equal to 2 by 2 plus 1 which is equal to 2 by 3 which is 0.66 which is equal to 66.66 percentage of power now is saved. Because you observed or not, yeah, in AM also, why the efficiency of AM is decreases? The efficiency of AM is decreases. The reason behind that, the carrier will take more power compared to sideband. That much of more power carried by carrier will be saved when it is come to the dsb-sc. That is the reason why the power efficiency in dsb-sc is 100%, because that much of power is saved and it is converted to sidebands. Okay, no doubt. Now we'll have another question. What is power saving in ssb-sc? What is power saving in ssb-sc when compared with AM? Now come to here. Now in AM, the power is distributed among 3 components, but in ssb-sc, power distributed in only one component, that is nothing but one sideband. So here 2 components is saved. So what is the saved component power? The saved component power is nothing but carrier power plus one single sideband power, whether it may be upper sideband or lower sideband, whatever it may be, okay, out of total power. So which is nothing but now the carrier component power plus what is the power taken by single sideband? Single sideband power is nothing but Pc into mu square by 4 by the total power. What is the total power? The total power in AM, which is nothing but Pc into 1 plus mu square by 2. Therefore, which is equal to Pc cancel and 2 is also cancel. Now this is nothing but 4 plus mu square by 4 plus 2 mu square. 4 plus mu square. Now Pc cancel by 4 and 2 plus mu square by 2 and 2 cancel. Therefore 4 plus 2 mu square is also a function of modulation index. Now what is the maximum power saving in ssb-sc when compared with AM? The maximum power saving in ssb-sc when compared with AM is 4 plus 1 by 4 plus 2, which is equal to now 4 plus 1, which is 5 by 6. Now this is a 5 by 6, which is nothing but 0.83. Now let us take this is 83%. Am I not? Yes. If you take only one carrier, 66% power you saved, but here one carrier and one sideband, 83% of power you saved. Maximum means I just put mu as 1. What is the meaning of maximum? Maximum means modulation index equal to 1. Okay, 100%. Okay. Now this is the power saving in ssb-sc when compared with AM. What is power saving in ssb-sc when compared with dsb-sc? Very simple question, right? What is power saving in ssb-sc when compared with the dsb-sc? There is no need to work also, okay? Because in dsb-sc 2 components, ssb-sc 1 component. Therefore, now 50%, 1 component you saved. So power saving is nothing but saved component is one single sideband out of total power. One single sideband, which is nothing but one single sideband power is Pc into mu square by 4. Now the total power will be equal to Pc into mu square by 2. Pc cancel. Now mu square cancel. 1 by 2, which is equal to 0.5, which is 50%. So the power saving is 50% in ssb-sc when compared with dsb-sc. Obviously 2 component, 1 component is saved, 50% power is saved. Okay. Now these are the power savings regarding power distributions and power savings in ssb-sc. But the important and heart of the modulation technique, any modulation technique, is bandwidth. What about the bandwidth in ssb-sc we will see. Okay. Now we will see the generation and as well as bandwidth calculations parallelly. So now in ssb-sc modulation, now I want to see here ssb-sc modulators. What are the different modulators to generate ssb-sc wave or ssb-sc modulation technique? There are two techniques here, two methods to generate an ssb signal. Now one method is based on frequency, therefore this is called as frequency discrimination method. Frequency discrimination method. And another one is based on phase, therefore that is nothing but phase discrimination method. One is based on frequency, another one is based on phase. This is phase discrimination method, and another one is frequency discrimination method. Okay, one is frequency discrimination method and the another one is phase discrimination method. Okay, there are two ways to find ssb-sc generation. One is frequency discrimination and the second one is phase discrimination. So now first we will see based on frequencies, therefore that is nothing but the frequency discrimination method. Now this is also called as frequency discrimination method, is also named as, now we will see the generation of ssb-sc based on frequency, and after that we will put an appropriate name for this frequency discrimination method. Is there any other alternate name which is suitable for frequency discrimination method also? We will verify. Okay. Now this is ssb-sc modulators. Now this is ssb-sc modulator. The ssb-sc modulators are frequency discrimination method and another one is phase discrimination method. Now this is the product modulator or balanced modulator. Now this is message signal and this is carrier signal. The message signal and multiplied with the carrier signal, now that is nothing but DSB-SC signal. That is nothing but a DSB signal. Message signal and multiplied with the carrier signal is nothing but a DSB-SC signal. Now we don't want a DSB-SC signal, we want a SSB, a single sideband. I don't want two sidebands, I want only one sideband. Am I not? Now see here. Now we'll see first frequency discrimination method. What is the frequency discrimination method? Now see here. For better understanding, I just write in frequency domain. Okay, this is the frequency domain. Spectrum. So what is there with us? Suppressed carrier and two sidebands. This is Fc plus omega, Fc minus omega. Now what is this? This is nothing but DSB-SC, double sideband suppressed carrier. Okay. Now this is Fc minus omega, Fc plus omega. Now this is a suppressed carrier. Now this is DSB-SC, two sidebands, but I want only one sideband. Therefore, now this is double sideband suppressed carrier is separated out by using a filter, band pass filter. Now this is the band pass filter. Now here I am using a band pass filter because I want only one sideband. Now see here, I just design a band pass filter with gain versus frequency characteristics like this. A pass band from, this is a gain versus frequency characteristics, this is a gain, this is pass band, and this is the stop band. Gain is multiplied with 0, pass band gain is multiplied with 1. This is Fc minus omega to Fc So now see here, now the band pass filter will allow only a pass band of fc minus omega to fc. So you can get the output of a band pass filter is, the output of the band pass filter is suppressed carrier fc minus omega to fc. This is upper sideband, only one sideband, which means this is a single sideband suppressed carrier with LSB, with lower sideband, only one sideband. So this is nothing but the output of the band pass filter is nothing but an ssb-sc signal or not? Yes, this is an ssb-sc signal. Now you identify here what is the bandwidth of ssb-sc. Now the bandwidth of this ssb-sc, which is nothing but the bandwidth which is equal to fc minus omega to fc. So fc minus of fc minus omega. Now this is bandwidth which is equal to omega hertz. So what is the bandwidth, which is a great achievement you are getting? The bandwidth of AM is 2 omega, bandwidth of DSB-sc is 2 omega, but the bandwidth of SSB-sc is omega hertz, which is reduced by 50% when compared with the bandwidth of AM and bandwidth of DSB-sc. So what is the main advantage of any communication technique, any modulation technique? The bandwidth of the modulated signal should be as minimum as possible, such that we can accommodate more number of signals. Am I not? Now see here, in AM to modulate a signal we require 2 omega hertz bandwidth. In DSB-sc 2 omega hertz bandwidth, but in SSB-sc to modulate a signal only a 50% of bandwidth is sufficient, omega hertz is sufficient. This is a great achievement that is possible in SSB-sc. Okay, so definitely there is a very good application or good advantage of SSB-sc is available for us. We will see that one also. Now first you see this one. But somebody's interest is not, sir, yes, we want a single sideband, but we want a upper sideband. We don't want lower sideband. No, not a problem. Then what should you do? So you design a band pass filter. You design a band pass filter with a pass band from. You design a band pass filter with pass band from fc to fc plus omega. Now this is a pass band, this is stop band, this is stop band. Now this is a band pass filter with a pass band fc to fc plus omega. So this is a now this is SSB-sc with upper sideband. Now this is the bandwidth of SSB-sc signal, which is equal to omega hertz. Now this is SSB-sc with upper sideband. SSB-sc with upper sideband, right? So there are only one sideband, whether it is upper sideband or a lower sideband. Okay. So now see here. Now this is a frequency discrimination method, because this is completely based on frequencies. So it is separated one sideband completely. Therefore, this is based on frequencies. Therefore, this method is named as frequency discrimination method. And another name for this is now based on filter, right? Based on filter, it is separated at one sideband out of two sidebands. Therefore, this is the frequency discrimination method, and it is also named as filter method. Filtered method. It is filter out one sideband completely from the two sideband. Therefore, this method is called as filtered method, or also called as frequency discrimination method. Filter out. Filtered method, or also called as frequency discrimination method. Okay. So what is the problem? Anyway, we can get the bandwidth which is omega hedges, which is reduced by 50% compared with the bandwidth of AM and dsb-sc. But the problem here is, now what happened? What is the disadvantage of this method is, the disadvantages of this method, frequency discrimination method disadvantage is, for separating one sideband from the two sidebands, we want to use a filter here, right? This is a band pass filter. This is the band pass filter, right? So if you see the band pass filter, now these are the band pass filter characteristics. What is the band pass filter characteristics? This is the sharp cutoff frequencies. Okay, this is the sharp cutoff frequencies filter is not available practically, because practical filters are having transition bands. So what is the disadvantages? The disadvantage of this frequency discrimination method is, as the practical filters are not having sharp cutoff frequencies, so it is difficult to separate one sideband completely. It is difficult to separate one sideband completely out of two sidebands. Now, because of the filter does not have a sharp cutoff frequencies, this filters having a sharp cutoff frequencies are nothing but ideal filters. The ideal filters will have a sharp cutoff frequencies and transition bands are zeros. What are the practical filters? The practical filters are like this. Then I just give the differences. This is gain versus frequency characteristics of ideal low pass filter. This is the ideal low pass filter. This is the ideal characteristics, but the practical characteristics are not like this. This is the cutoff frequency. This is the pass band. Okay. Now the practical filters are not like this. The practical filters will not have a sharp cutoff frequencies. The practical filters will have some transition band. This is transition band. Now this blue line is nothing but an ideal filter. This is the ideal filters will have a sharp cutoff frequencies. This is the ideal band pass, ideal low pass filter, ideal filter characteristics. Now this is a practical filter characteristics. This is practical filter characteristics. This is the practical filter characteristics and this is the ideal filter characteristics. This is the difference, okay, between the practical filters and ideal filters. Ideal filters are filters sharp cutoff frequencies. For ideal filter, transition bands are zeros. For ideal filters, transition band is 0 hedges. So it does not existing. This is the ideal case. Okay, practically it does not existing. The practical filters will have some transition bands that is available. So if have this particular practical filters are used here, what happen? If the practical filters are used here, this practical filters will have this type of a transition bands, but it will not separated one complete sideband. So part of another thing is also coming, right? These are the practical filters. It will not completely separated one sideband. That's what I mentioned here. As the practical filters are not having sharp cutoff frequencies, so it is not possible to separate one sideband completely. It is difficult. Okay, that is a disadvantage of this method. And students are asking that, sir, if it is disadvantage of this particular practical filters, then you go for any other alternate method. Yes, we go for the generation of an ssb-sc signal with the another method is also available. The another method is nothing but a phase discrimination method. Okay, so this is the practical and ideal filter characteristics. It does not existing and it existing practically. Okay, and transition band is changing is changing by changing the order of the filter. The transition band is changing by changing the order of the filter. So by change the appropriate order such that this transition band will be changed and minimized such that whatever the component we can have, we can select it. Okay, but here definitely one ideal case is required because a sharp cutoff frequency is required. That is not possible. So this is the disadvantage of this method. We can overcome this disadvantage by going for another method is nothing but a phase discrimination method. Okay, first you note down that, we'll see. Now the second one is phase discrimination method, right? Another way to generate an ss-based signal is phase discrimination method. Now this is the message signal. This is product modulator 1. Now the output of this product modulator 1 is AC m of t cos 2 pi fct. Product modulator 2. This is product modulator 2. Now this m of t. Now this is the Hilbert transform or a 90 degrees phase shift. You know that. Now this is nothing but m cap of t. Now this is nothing but AC m cap of t. Now here is also I just use a phase shifter because this is already saying that this is a phase shifting method. Phase shifters are used here. 90 degrees phase shifter. Now this is AC m cap of t. Now this is AC sin 2 pi fct. Now these two outputs of product modulators 1 are connected to a subtractor circuit. Now this is nothing but AC m of t cos 2 pi fct minus AC m cap of t sin 2 pi fct. Now this is passing through an amplifier of having a gain which is equal to 1 by 2. Then you can have an exact equation. Okay, for that I am using this scaling. So this is nothing but AC by 2 m of t cos 2 pi fct minus AC by 2 m cap of t minus AC by 2 m cap of t sin 2 pi fct. This is, if this is an adder circuit, this is plus. Now what is this? This is nothing but an ssb-sc signal or not? This is ssb-sc modulated signal, where this minus is nothing but upper sideband, where this plus is nothing but lower sideband. Okay. Now this is an ssb-sc signal, but this is based on phase. Phase shifter is used. Hilbert transform means again it is also a phase shifter. Okay. This is totally based on phase shifting. Therefore, this method is nothing but phase discrimination method. Here there is no need to see the filter. There is no shortcut cutoff frequencies, no sharp cutoff frequencies, transition bands. All these things are not required. Now generate these two phase shifters and you can get the appropriate product modulators, and appropriate adder or subtractor circuit is used, and you can get an ssb-sc signal. Okay, this is another way to generate an ssb-sc signal. Now one is nothing but frequency discrimination method, another one is nothing but the phase discrimination method. This is the phase discrimination method to generate an ssb-sc signal. Note.